In this video, I will talk about quadratic functions and models. Here are the course objectives: analyzing graphs of quadratic functions, write quadratic functions in standard form and use the results to sketch graphs of functions, and then find minimum and maximum values of quadratic functions in real-life applications. Here we study the graphs of polynomial functions. So generally speaking, polynomials are general names of functions. So previously you knew that linear functions exist, and we talked about types of linear functions, things like constant function, horizontal function, vertical function, vertical equation, and things like that. But we also learned about squaring function and like some of the other parent functions. So these are basically examples of polynomial functions. Polynomial is a general term that we're going to define what it is in the next slide. So polynomials are more like an umbrella term for functions. So here's the definition of polynomial function. Let n be a non-negative integer and let a sub n minus 1, a2, a sub 1, a sub 0 be real numbers with a of n not 0. So then the function f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 all the way to a1x plus a0 is called a polynomial function of x with degree n. So you guys realize n is the exponent of the biggest a of n, and then a of n, a sub n, is what we call leading coefficient. It's basically the number that we multiply the x that has the higher n. So we classify functions using the degree, which is the n or the exponent. So for instance, a constant function, f of x equals c, has a degree 0 because it does not have any x. And a linear function like ax plus b has a degree 1 because we know that a of x has a times x to the 1. We generally don't use 1 as an exponent, we just write x, but it actually has an exponent to be 1. So in this specific section, you will study second degree polynomials, which is what we call quadratic functions. So in this video, we'll focus on quadratics. So here are some examples of quadratic functions. So you guys realize f of x equals x squared plus 6x plus 2, or you may see some different variations that look a little bit different. So here we have 2 times x plus 1 squared. Because this thing is squared, x is going to be squared, so that's how we know it's a polynomial. Here, h of x has square already, k of x has negative 3x squared, and then here, m of x, it looks a little bit different, but eventually when you factor this guy out, you're going to see something like x squared plus dot dot dot, like all the other terms will show up, and that's how we know this is a quadratic because it's been multiplied. All right, so specifically defining what a quadratic function is, we're going to say let a, b, c be real numbers with a is not 0. Then the function f of x equals ax squared plus bx plus c. This is called quadratic function. And then this format is generally what I call general form. So I'm going to call this general form of quadratic functions. The graph of a quadratic function is always a U-shaped curve, which is what we call parabola. And parabolas occur in many real-life applications, especially those involving reflective properties of satellite dishes and flashlight reflectors. We know that all parabolas are symmetric with respect to a line called axis of symmetry. And then the point where the axes intersect with the parabola is what we call vertex. And then you guys see we have two different cases. On the left hand side, we have the leading coefficient to be positive. What I mean by that is I mean a is positive. So here whatever x squared term has, whatever number it's been multiplied by, that's what we call a, or the leading coefficient. And so in the second case, if e is negative, then we're going to say that has to open downward. So depending on what a is, if a is positive, then parabola opens up. If a is negative, then parabola opens down. So those are the two scenarios. Whenever a is positive, then vertex is the lowest point. Whenever a is negative, then vertex is the highest point. The simplest type of quadratic function is f of x equals ax squared. So the graph of this is basically a parabola whose vertex is 0, 0. And as you can see in the graphs, it's always going to have a vertex at the origin, or 0, 0. And then whenever a is positive number, then it opens up. Whenever a is negative, then it'll open down. As you can see here on the right hand side, it opens down. So let's take a look at an example. Sketch the graph of each quadratic functions and compare it with the graph of y equals x squared. You guys realize this is what I call the parent, or the squaring function. Squaring function. So in the first case, we have f of x equals 1 over 3 x squared. We know that the parent function x squared looks like something like this gray line, and then 1/3, it looks like shrinked version of x squared, and so it's like wider, and so it has a vertical shrink. So this one has a vertical shrink. And this is something familiar with us because we learned about that during transformation chapter a while ago, where if the outcome, or the y value, is manipulated by numbers that are between 0 and 1, then it's going to always shrink because you're basically dividing it. The second case, where we have 2x squared, this one is going to stretch by a factor of 2 because it's multiplied by 2. So g of x equals 2x squared is going to look something like this because it's been multiplied by 2. It's going to have a vertical stretch. All right. So again, keep that in mind, that the graphs of y equals f of x plus minus c, y equals f of x plus minus c, or y equals f of negative x, y equals negative f of x, are transformations of the graphs of any types of functions. We learned that previously. So here are a couple of examples where you see that parabolas are being basically shifted or transformed. So on the left-hand side, as you can see, x squared is shown in gray, and then this other function seems to have flipped or reflected by the x-axis because it has the negative right here, and then it's been shifted 1 unit to the up because it adds 1 to that whole thing, so that's why it's been shifted 1 unit above. On the right hand side, you guys can see x, the input, is being added by 2, so that's why the function moves to the left side, and then it subtracts 3 from the whole thing, so that'll shift it downwards 3 units. So now we're going to take a look at what we call the standard form of a quadratic function. So the standard form, in some books or other resources, it's called the vertex form because it specifically or explicitly tells you what the vertex is. So that function looks like f of x equals a times x minus h squared plus k. So this is very convenient, especially for sketching, because again, we'll figure out what the vertex is, and vertex is always h, 0. So you're going to take a look at the function, and then you're going to say, well, h is right here, k is right there. So h is going to be the x coordinate of the vertex, K is the y coordinate of the vertex. X coordinate, y coordinate. So this is X, this is Y. Okay. All right, so next thing we're going to talk about is using standard form to graph a parabola. So you guys realize the given function has f of x equals 2x squared plus 8x plus 7. So this does not look like the standard form we saw earlier. So this looks more like the general form. General form. So what we like to do is to convert this into something like a of x minus h squared plus k. You guys realize this is what we call the standard form. So this is the standard or the vertex form. So this is standard form. The way we convert this is we use this idea called complete the square. So you may remember from your previous algebra knowledge, we're going to use complete the square to convert from general form into the standard form. So the way we do that is, I'm going to do that step by step. So we write out the original equation. Then we factor out the 2 out of the x terms because we want the x to have a coefficient of 1. We just want to isolate x squared term. So we take out the 2. So it'll look like 2 parentheses x squared plus 4x. So we divide this because now we're multiplying that by 2. The next thing we're going to do is we're going to add and subtract 4 within the parentheses. The part of the reason is that the rule for completing squares is that you always add and subtract b over 2a. So this is what we basically did. So by a and b, I mean with the given function, you guys realize the leading coefficient is 2, so that's my a. This guy is my b. Or sorry, not here. I'm going to go back. Right here, this guy. So I'm going to say a is 1, b is 4. So I'm gonna compute b over 2a. So then b is 4 and a is 1. So I'm gonna do 2 times 1. So that'll give me 2. Oh, squared. I need to square this guy. Yeah, b over 2a squared. So then this will give me 4. So 4 is the amount I need to be adding and subtracting, which is a little bit silly, but it's going to be extremely helpful. So then what we're going to do is the negative 4 right there can be removed from the inside because of the 2 outside of the parentheses. Then we must multiply negative 4 by 2 as shown below because this guy is right there. So we have to distribute the 2 to negative 4. And then once we do that, it looks like this. So the outside you'll get negative 8 and then plus 7 was already there. So then add that up and then you get negative 1. So as you can see, the whole thing now looks like the standard form. And then here you can tell the vertex is h. So you guys realize the standard form always looks like a times x minus h squared plus k. So for that reason, because this is negative right there, you have to convert this guy into something like 2x minus 2 because it's positive, then plus k, which is like plus negative 1. So this is h, this is k. And then the graph is given. All right, so next thing we're going to talk about is x-intercepts of these quadratic functions. So that's an important concept. To find x-intercept, as you guys remember, we let the function go to 0 because when any type of function crosses the x-axis, the y value has to be 0. And then also we call x-intercept to be zeros as well. Zeros, it's the same thing. Sometimes you cannot factor these functions. In those cases, you use the quadratic formula. Quadratic formula help you find the x-intercepts of any carbon function. So it might be useful for you to remember what quadratic formula looks like. So the way a quadratic formula looks like is something like x1 comma 2 is always equal to negative b plus minus square root b squared minus 4ac over 2a. And then lastly, you need to note that a parabola may not have x-intercepts. So not every parabola has x-intercepts. Next, we're going to talk about is minimum and maximum values of functions. So the way we find that is we take a look at the vertex. So the way we find the vertex is we use this formula, negative b over 2a and f of negative b over 2a. So you guys realize this is actually h, this is hk. So the x value of the vertex, y value of the vertex. So using that, we can find the minimum and maximum values of a function. Here's an example. The path of a baseball after being hit is given by the function f of x equals negative 0.0032 times x squared plus x plus 3. You guys realize that this is a quadratic function. Quadratic function. Part of the reason is that it has the exponent n to be 2. So the exponent is 2. And then this function represents the height of the baseball, and x is the horizontal distance from the home plate. So x is the distance, and then based on that, we're going to try to figure out the maximum height of the baseball. So the way we're going to look at is we're going to take a look at A, B, and C, and then realize in this case A is that decimal number, negative 0.00 right there, and then b is this guy, so x is b multiplied by 1 because it's like 1 times x, so b is 1, a is that. So then we'll use that negative b over 2 thing to be able to find the x. So this is for the x value of the vertex. So we compute that and we get 156.25. So that gives you the distance. And then to find the maximum height, we put that into the function because f of negative b over 2a is going to give you the maximum height. So you put this into right here, and then you get 81.125 feet. And then next thing we're going to talk about is the factored form of quadratics. So we previously learned the general form, which looks like ax squared plus bx plus c. We sometimes factor this and then get something like f of x equals a times x minus x1 times x minus x2 to find the x-intercepts. So again, we do that for the ones that are factorable. So again, some quadratics are not going to have factors like this. It's not going to be easily factorable. So in this example, I'm going to show you how to do this one. So we have f of x equals negative x squared plus 6x minus 8. So the way I'm going to do that is I'm going to compute, I'm going to find two integers that multiplies to negative 8 and then adds to 6. So I need two integers that multiplies to negative 8 and then adds to 6. So generally speaking, we need to we think about it and then we need to find a way to do that. So that's gonna be 4 and 2 because 4 times 2 is 8. 4 plus 2 is 6. So 4 and 2 are then two integers that we're gonna need. And then using those two integers, what I'm gonna do is I'm gonna split the b term, the middle term. So I'm gonna say negative x squared plus 4x plus 2x minus 8. So that is the same thing as my function. So then here I'm going to group these guys, the first and the second, and the third and the fourth. So then I'm going to find the common term. So x squared and 4x has x in it. So I'm just going to factor out as like negative x. So in that case, it'll be something like x minus 4. Because negative x distributed into x minus 4 gives you negative x squared plus 4x. And then 2x and negative 8 has 2 in common. So 2 times x minus 4. So now I have these two guys in common, x minus 4. So then I'm going to say, well, this guy looks like factor out the x minus 4 times negative x plus 2. So these are my factors. And then x-intercept specifically are the things that solve these things. So then there are two options. So x minus 4 could be 0, or negative x plus 2 could be 0. So in that case, x is 4. So this is x1, let's call it x1. And then this thing can be 0 when x is 2. And that's going to be the second x-intercept. So there are two x-intercepts. One is 4 comma 0. The other one is 2 comma 0. So basically, those are the points where this parabola passes the x-axis. Like I can have a rough graph here. Well, let me do a better one. So then this function is gonna probably look like, so 2 and 4. Because the a is negative, it's gonna look downward. So it's gonna probably look like this. Sorry about my bad graph. So, and then we're gonna note some quadratics are not factorable. In that case, you can use the quadratic formula as I mentioned earlier. Lastly, to conclude this video, I'm gonna summarize quadratic functions. So general form of quadratics look like f of x equals ax squared plus bx plus c, where a is not 0. So a, b, c are real numbers and a is not 0. So any real numbers but not 0, that's what we call general form. Standard form or vertex form always looks like f of x equals a times x minus h squared plus k, where h comma k is what we call vertex. And then factored form always looks like f of x equals a times x minus x1 times x minus x2. And then the cool thing about this form is that x1 and x2 are the zeros or x-intercepts or zeros. And yeah, that concludes this video.